Hello students, Callie Daniels here. In this video we'll solve applications of rational expressions. We'll continue to use our same six-step process that we've used previously. We'll read the problem carefully, assign a variable to represent the unknown value, use diagrams, tables, and/or pictures as needed. If necessary, express any other unknown values in terms of the variable. Step 3, we'll write an equation using the variable expression or expressions. Step 4, solve the equation. Step 5, state the answer. Does it seem reasonable? Step 6, check the answer in the words of the original problem. In example 1, we're going to solve a problem about an unknown number. A certain number is added to the numerator and subtracted from the denominator of 5/8. The new number equals the reciprocal of 5/8. Find the number. Well, let's define our unknown, or let x represent the unknown number. We've assigned the variable x. Now let's write an equation. We're starting with the fraction 5/8, and we know that a certain number is added to the numerator. So in the numerator we add x, and it is subtracted from the denominator. So 8 minus x in the denominator, and we know that this new number equals the reciprocal of 5/8, which is 8/5. Now let's solve our equation. This is a proportion, a fraction set equal to a fraction, so let's cross multiply. 5 times 5 plus x is equal to 8 times 8 minus x. Distributing, we have 25 plus 5x is equal to 64 minus 8x. Let's add 8x to each side and subtract 25. 64 minus 25 is 39. Divided by 13 is 3. X is equal to 3. Now let's check that and see if it makes sense. In our original equation is 5 plus 3. 5 plus 3 over 8 minus 3 really equal to 8/5. And we can see that it is indeed a true statement. 8/5 is equal to 8/5. So the number 3 should be added to the numerator and subtracted from the denominator of this rational expression. Well, let's look at another example. Example 2, solving a problem about distance, rate, and time. And let's just recall the formula: distance is equal to rate times time. We're going to need that. A boat can travel 10 miles against a current. In the same time, it can travel 30 miles with the current. So it can go further with the current because the current is helping it move along at a faster rate. Okay, I'm going to start by organizing our information in a table. The distance against the current is 10 miles, but with the current is 30 miles. We know that the current flows at a rate of 4 miles per hour. We want to find the speed of the boat with no current or in still water. So let's assign our variable, letting x represent that unknown, the speed of the boat with no current. Now, as the boat travels against the current, it is the speed of the boat minus the current, 4 miles per hour. But with the current, the boat travels faster. It travels its speed plus that speed of the current. Now we want to complete this time column, and we're going to use the formula distance is rate times time in a different form. Okay, if we divide each side of this equation by r, the rate, then an equivalent form is time equal distance divided by rate. So we don't know how much time it took for the boat to travel the 10 miles against the current, but we do know that the time is distance 10 divided by rate x minus 4. Similarly, for the time with the current, the distance 30 divided by the rate x plus 4. Now we want to write an equation, and it's going to come from this time column because we know that those times are the same for these two situations. So we know that the time 10 divided by x minus 4 is equal to 30 divided by x plus 4. And we have a proportion here, therefore we can cross multiply to solve. Let's write 10 times x plus 4. Set that equal to 30 times x minus 4. And continue to solve. Distributing, on the left we've got 10x plus 40. On the right, that's 30x minus 120. Subtract 10x from each side. Add 120 to each side. We've got 160 is equal to 20x. And dividing by 20 gives x is equal to 8. So we believe that the speed of the boat with no current then is 8 miles per hour. Now let's check this. In our original equation is 10 divided by 8 minus 4 really equal to 30 divided by 8 plus 4? Are these times truly equal? That is 10 fourths equal to 30 twelfths? Reducing, dividing the left top and bottom by 2 gives 5 halves. On the right, there's a common factor of 6. Dividing that out also gives 5 halves. So the time traveling against the current and with the current, both those scenarios is 5 halves of an hour. You might say 2.5 hours. And that checks out just fine. Example 3 is similar. It's also a distance, rate, and time problem. Here we have a man, Vince, can fly his plane 200 miles against the wind. Let's put that distance in our table. In the same time, it takes him to fly 300 miles with the wind. So he can fly a further distance with the wind because it's helping him go faster. The speed of his plane in still air is 150 miles per hour. Now, in this situation, we want to find the speed of the wind, okay? And so let's talk about those rates. Against the wind, the speed of the plane minus the wind, 150 minus x. The order that you do your subtraction there matters, okay, because subtraction is not commutative, and that's the speed of the plane minus wind in that order, okay? With the wind, 150 plus x, the speed of the wind. Time is distance divided by rate. So the time against the wind is distance 200 divided by 150 minus x. With the wind is 300 over or divided by 150 plus x. Again, we know that these times are the same. In other words, they are equal. So 200 divided by 150 minus x is equal to 300 divided by 150 plus x. And once again, I'm going to cross multiply. Let's take 300 times 150 minus x, set that equal to 200 times 150 plus x. And let's distribute. 300 times 150 is 45,000 minus 300x. 200 times 150, that's 30,000, and plus 200x. I'm going to add 300x to each side. I'm going to subtract 30,000. And dividing by 500 gives x equal 30. And so the speed of the wind, let's add our units on there, 30 miles per hour. And I'm going to let you check that one. Just check it by substituting 30 into that original equation for x and make sure that you get a true statement. You can do that one. Now let's take a look at our next concept, work rate and time applications. Let's do some prep work. If a job can be completed in t units of time, then the rate of work is 1 over t of the job per unit of time. For example, it takes Tanya 3 hours per evening to complete her homework. Thus, her rate of work is 1 over 3, or 1/3 of the job per hour. So the rate is given per unit time by finding the reciprocal of the time it takes to do the job. Second example, Jim can complete the job of mowing his lawn in 4 hours. Thus, his rate of work is 1/4 of the job per hour. Another note, the amount of work completed is equal to the rate of work times the amount of time, or work equal rate times time. And this looks a lot like distance equal rate times time, doesn't it? In fact, those formulas are very similar. With work, a job is being completed, and with the distance, a distance is being traveled. So let's come back and relate an example to our previous example. Okay, so if Tanya works for 2 hours and her rate of work is 1/3 of the job per hour, how much of the job has she completed? Well, work is rate times time. In other words, 1/3 of the job per hour times 2 hours worked. Well, she's completed 2/3 of the job in those 2 hours. And in part B, if Jim's rate of mowing the lawn is 1/4 of the job per hour and he works for 2 hours, how much of the job is completed? Well, work is rate times time. And Jim's rate is 1/4 of the job per hour times 2 hours. That's 2/4, or 1/2 of the job is complete. Well, let's just add a little bit to this. How much of the job would he complete in 3 hours? Well, 3/4 of the job. And lastly, how much would he complete in 4 hours? Well, 1/4 times 4 is 1, okay? He would complete 1 full job. He would finish mowing the lawn, wouldn't he? All right, I think we're ready to work an application. Example 4, solving a problem about work rates. Al and Mario operate a small roofing company. Mario can roof an average house in 9 hours. Al can roof a house alone in 8 hours. How long will it take them to do the job if working together? Let's let T represent that question, the time it takes for Al and Mario to complete the job working together. And so we know that they're both working for that same amount of time, T, and we'll put that in our table. Now let's get the rates. Mario can roof the house alone in 9 hours, therefore his rate is 1/9 of the job per hour. Al can do this job in 8 hours, therefore his rate is 1/8 of the job per hour. Work is equal to rate times time, so the amount of work done by Mario is 1/9 times T. The amount done by Al is 1/8 times T, and together they will complete 1 full job. And so our equation comes from this last column where we add the amount of work done by Mario, 1/9 T, plus the amount of work done by Al, 1/8 T, is equal to 1 complete job. And work problems are set up all very similar to this statement right here. Well, let's solve this equation. I'm going to multiply each term by 72, the lowest common denominator. 72 times 1/9 is 8t. 9 divides into 72 8 times. 72 times 1/8 is 9. That's 9t. 8 divides into 72 9 times. And don't forget, 72 times 1 is 72. That's 17t equals 72, or our time is 72/17. That's an okay answer. It is reduced if you want to write it as a mixed number and divide 72 by 17. That's going to go in there 4 times. With 4 remaining, so you can write that 4 and 4/17 hours. Quick check. Substituting into the original equation is 1/9 times, I'm going to use our improper fraction 72/17 plus 1/8 times 72/17 really equal to 1. In other words, is 8/17 plus 9/17 equal to 1, and it is, and that's going to check out just fine, isn't it? Last problem. Example 5, another work rate and time problem. An inlet pipe can fill a swimming pool in 9 hours, and an outlet pipe can empty it, or let's say drain this pool in 12 hours. But through an error, both pipes were left open. So how long will it take to fill the pool? Don't make this error, okay? Don't fill your pool and leave the drain open. Well, let's let T represent the time it takes for both pipes to fill the pool working together. So that goes in our time column. Next, let's input our rates. The inlet pipe can fill the pool in 9 hours. Its rate is 1/9 of the job per hour. The outlet pipe can empty the pool in 12 hours. Its rate is 1/12 of the job per hour. Work is rate times time. How much work does the inlet pipe do? 1/9 times T. Outlet, 1/12 times T. And that should complete one full job. But with this problem, we're not actually going to add those amounts of work because they're working in opposite directions, okay? The inlet pipe is filling, the outlet pipe is removing, and so the amount of work done by the inlet pipe to fill the pool minus what's done by the outlet pipe, because it's taking away the water, isn't it? Okay, 1/12 T equal 1. Now let's multiply by our LCD, which is 36, as we look at 9 and 12. That's the smallest number that both 9 and 12 divide into. 1/9 times 36. 9 divides into 36 4 times, 14. 1/12 times 36. 12 divides into 36 3 times, 3t. And that's equal to 36. In other words, T equal 36 hours to fill the pool. Yikes. And let's check this and see what's happening here, okay? Checking in our original equation. 1/9 times 36 minus 1/12 times 36. Is that equal to 1? In other words, is 4 minus 3 equal to 1? Sure it is. And what's happened here is that in this 36 hours, the inlet pipe has put in enough water to fill that pool 4 times, while the outlet pipe has taken out enough water to empty it 3 times. Filling it 4, emptying it 3 leaves us at 1 complete job. All right, there you go, students. In this video, we have solved applications of rational expressions. Good luck on those.